We're on lesson 2 of chapter 10, which we're going to use measures of central tendency and dispersion. First, we're going to compare measures of central tendency. Then we're going to compare measures of dispersion. First, we're going to define these two words, central tendency and measure of dispersion. The central tendency is the central or typical value for a statistical distribution. You probably learned these before. There's the mean, the median, and the mode. The mean stands for the average of the numerical data, found by this formula, x with a line over it, which represents mean, equals the values of the numbers, divided by the amount of numbers, n, the number of numbers. The median is the middle. It's the middle number when the values are written in numerical order, from least to greatest. Then the mode is the value that occurs most frequently. When you're looking for measures of dispersion, you're looking for how the data is spread out. Is it evenly spread? Is it taking big jumps in between the data? That's what this will tell us. The range will tell us the difference of the greatest value and the least value, so that tells you dispersion. This also tells you dispersion, the mean absolute deviation. That's the average distance of the data from the mean. And in the formula where you find it, you find the absolute value of the distances away from the mean and divide it by the amount of numbers in the data set. First, we're going to find central tendency measures. So it says the height in feet of 8 waterfalls in the state of Washington are listed below. Which measure of central tendency best represents the data? Explain your reasoning. So here they're listed in least to greatest already, so that helps us quite a bit. If they're not listed in least to greatest, it's always good to do that. So the ones that will be pretty easy to find right now will be the median and mode. The mode is the value that occurs most frequently. Well, I see two number 1000s, and none of these other numbers repeat, so these will be our mode. We'll say mode equals 1000. We can find the median by working our way to the middle. So we cross off the outside 2, the next outside 2, the next outside 2, and we're left with two numbers. Whenever that happens, we need to find the average of these two, so add them together and divide by 2 because there's two numbers. So 1191 plus 1200 divided by 2, so our median becomes 1195.5. Now we're going to look for that mean. So the mean, we follow that formula where we add all the numbers together and divide by the number of numbers. So if we get our calculator out for that, we have 1000 plus 1000 plus 1181 plus 1191 plus 1200 plus 1268 plus 1328 plus 2584 divide by the total number of numbers, and that gives us a mean of 1344. So mean will say 1344. So it asks us a little bit of a vague question. Which measure of central tendency best represents the data? That means which of these numbers really fits in with the rest of the numbers. Well, if you're going to look at mode, that one is at the way bottom of all this list. So I would say that the mode doesn't really represent this data very well. The median, however, would fit pretty much right in the middle like it usually does, and that's usually a good indicator. And a lot of these numbers around that look pretty close to this number. The mean, on the other hand, would fit way over here, and it's really only close to a couple of these numbers. The reason for this is this large number here, the 2584, really brought that mean up. And that's what kind of makes it a little bit distant from these other numbers here. And that makes our median the best measure of central tendency. If I had to explain my reasoning, I would say that the mode is significantly less than the rest of the data, and the mean is significantly more than the rest of the data. Now we're going to compare measures of dispersion. Remember, measures of dispersion are the range and the mean absolute deviation. So it says the top 10 finishing times in seconds for runners in two men's races are given. The times in a 100-meter dash are in set A, and the times of the 200-meter dash are in set B. Compare the spread of the data for the two sets using A, range, and B, the mean absolute deviation. Remember, the range is the easier one to find. So set A is the 100-meter dash, set B is the 200-meter dash. So the best time was 10.62, and the worst time was 11.32. So to find that, we could say 11.32 minus 10.62. So there's a difference of 0.7. We'll say R for range, 0.7. If we find the range for set B, then the lowest number is 21.37, and we have 22.73. So we could do 22.73 minus 21.37, and that gives us a range of 1.36. So R is 1.36. Now we're going to find the mean absolute deviation. Remember, that's finding the average distance of the data from the mean. We use absolute value here because all that matters is how far away it is from the mean. It doesn't matter if it's under or above it. The only thing that matters is the distance from that mean. So first we need to find the mean of each data set. So let's do that. We have 10.62 plus 10.94 plus 10.98. And that gives me this total number. I need to divide that by 9. That gives me 11.08. We'll round that to the nearest hundredth. So for mean, we'll say 11.08. Let's find the mean for this data set then. 21.37 plus 21.4. And that gives me a mean of 22.23 if we round that. So here we see the mean in this case goes around here. The mean in this case comes around here. Remember, the mean absolute deviation is the average distance of the data from the mean. So whether it's under or over, it's still going to count the same. So if we paste that formula onto here, we can follow that. So x1, which is 10.62 minus the mean, take the absolute value of that. So 10.62 minus 11.08, that's negative 0.46 or positive 0.46. So 0.46 is our first number. We have 10.94 minus 11.08, that's negative 0.14 or positive 0.14. We have 10.98 minus 11.08, that's negative 0.1 or positive 0.1. I can do these ones in my head. 11.05 minus 11.08 would be negative 0.03 or positive 0.03. Now we have 11.13 minus 11.08, that's positive 0.5. Absolute value of that would remain the same. Positive 11.15 minus 11.08 would be positive 0.07. 11.28 minus 11.08 would be positive 0.2. 11.29 minus the mean would be positive 0.21. 11.32 minus the mean would be positive 0.24. So we need to add up all these different absolute values and divide by the total amount of numbers, which would be 9. 0.46 plus 0.14 plus 0.1 plus 0.03 . So we end up with 1.5, divide that by 9, that'll give us 0.167, we'll say. So the deviation equals 0.167. So here the mean was 22.23. Let's write this in blue just to differentiate here. So we need to find all these different numbers as well. So 21.37 minus 22.23, absolute value of that would be 0.86. Now we have 21.4. Negative 0.83. So we have positive 0.83. 22.23 is exactly 22.23, so we could put a 0 there. We have 22.34, that's a difference of 11, 0.11. Another one of that's exactly the same, so another 0.11. 22.36 and 22.23, that's 0.13. 22.6 and 22.23, that's a difference of 0.37. 22.66 would be a difference of 0.43, and 22.73 would be a difference of 0.5. So if we add all those together then, 0.86 plus 0.83 plus, we can skip the 0, 0.11 plus 0.11 plus 0.13 plus 0.37 plus 0.43 plus 0.5 and divide that by the total number, which would be 9. That gives us a mean deviation of 0.371, we'll say. So not only is the range bigger for the 200-meter race, but the mean deviation, or the average distance from the mean, is much greater as well. And that would make sense. The longer the race becomes, the further apart you're going to have the runners be. If you think about a mile race, there you have actually much longer distances of finishers than the 100-meter dash, where they all finish pretty close to each other.